You sit there, your fingertips trembling mere millimeters from the keyboard. It's late. So late, even the moon seems to have gone to rest. All that illuminates the room is the light from a blank document facing an equally blank stare. This is not an unfamiliar sight. Not to you. The cursor flickers restlessly, as if to express its eagerness to flow down the page. Like old times, you think to yourself. You too had this eagerness once. You've been toiling over a mathematical proof for a very long time. Has it been months? Years? If you're an undergraduate of math, it might have even been days. You let out a heavy sigh. I've tried everything, you whisper. You think of all the giants before you that you feel you have let down. Grothendieck, Gauss, Gödel. You stop. Gödel. Of course. Maybe the reason you've been having so much trouble is because of the inherent incompleteness of our mathematical foundations. You might have heard of problems like the continuum hypothesis before, well known because it cannot be proven nor disproven from the usual foundations of mathematics. The first time you hear about this kind of result, it may seem like nonsense. The continuum hypothesis is a yes-no question about the existence of a subset of real numbers of a certain size. Either such a set exists or it doesn't. How can it be neither true nor false? This is a misconception. The independence result doesn't say anything about whether the continuum hypothesis is true or not. What it does say is, if the continuum hypothesis is true, we cannot hope to use the usual axiomatic foundations of set theory to provide a proof, and if the continuum hypothesis is false, we cannot hope to build a counterexample. Even after you understand the statement of the independence result, you may find yourself questioning your philosophical perception of mathematics. I thought mathematics describes an absolute truth. I thought mathematics is discovered, not created. I'm not a philosopher, so I won't pretend I have a well thought out response to this. However, there is a lot of insight to be gained from understanding how we show something cannot be proven nor disproven. From there, maybe you can come to your own conclusions about the philosophical ramifications of independence results. I don't intend to give a full proof of the independence of the continuum hypothesis. The reliance on model theory or any substitute heavily distracts from the big idea. Rather than studying ZFC, which is the usual axiomatic foundation of set theory, let's work with a toy theory, a theory of integers. Let's lay down the ground rules for our theory of integers. First of all, there should be an element called 0. Having nothing is a good place to start. We should probably also require an element called 1, and maybe let's assert that 0 and 1 should not be the same thing. To allow us to build larger integers, let's define an operation plus called addition. I want addition to look like the addition we're used to, so let's assert that addition must be associative, commutative, and 0 should be a neutral element. To allow for negatives, let's say for every element A, there should be another element B such that A plus B equals 0. Such a number B would be uniquely determined by A, so we can call this thing negative A. Addition is great, but we should also implement another operation, dot, called multiplication. Multiplication should also be associative and commutative, and 1 should be the neutral element in this case. Addition and multiplication should behave nicely with each other. This means that multiplication should distribute over addition. Finally, let's say that if A is not 0 and B is not 0, then A times B should also be non-zero. The cognoscenti among you may recognize these axioms as those of an integral domain. Just to see how we can build integers out of these axioms, we already have an integer 0 by axiom 1 and an integer 1 by axiom 2, so we can use addition to build the natural numbers in an integral domain. Define 2 to be 1 plus 1, 3 to be 1 plus 1 plus 1, and so on. Moreover, from axiom 3d, we can build the negative numbers. We know that there must exist a number negative 2 with 2 plus negative 2 equals 0. We must also know there's a number negative 3 with 3 plus negative 3 equals 0, and so on. Consider the statement x plus y all squared is equal to x squared plus 2xy plus y squared. This statement is true for all x and y, and we can use the axioms of an integral domain to prove it. Using distributivity, we can expand the left-hand side as x plus y times x plus x plus y times y. Then, using commutativity of multiplication, we can move the x and the y to the left of x plus y. Now we can again distribute x and y over their respective sums x plus y. Finally, using commutativity again, we can swap y times x with x times y, and that completes the proof. What I'm trying to say with this example is that the easiest way to show that something is provable is to just provide a proof. Now that we have some idea of what a proof looks like, how do we show that a statement is not provable? Well, consider the very similar statement x plus y all squared is equal to x squared plus xy plus y squared. This statement is unprovable from the axioms, and we can show this by proving that a statement is actually false. Specifically, let x equal 1 and y equal 1. Then, the left-hand side expands to 4. On the other hand, the right-hand side expands to 3. If the alleged statement were true, this would mean that 4 equals 3. By adding negative 3 to both sides, this would mean that 1 equals 0. However, this directly contradicts axiom 2, which says that 0 and 1 are not the same number. Therefore, this statement is false. In particular, it cannot be proven. That's cheap. False statements are obviously unprovable, I hear you complain. How does this help us show that the continuum hypothesis is unprovable if it's also impossible to prove that the continuum hypothesis is false? Surprisingly, it helps a lot. Consider now the infamous freshman's dream. X plus y all squared is equal to x squared plus y squared. Well, clearly this is false, so I don't see your point. Okay, so let's try the same approach as before. Let x equal 1 and y equal 1. As before, the left-hand side expands to 4. On the other hand, the right-hand side now expands to 2. If the freshman's dream were true, then this would mean 4 equals 2. By adding negative 2 to both sides, this would mean that 2 equals 0. Contradiction?
I think not! What the f***?
Obviously 2 equals 0 is false. Is it though? The statement 2 equals 0 doesn't actually directly contradict any of the axioms of an integral domain. However, we do have a specific definition of integers that we've learned since grade school. We learned how to count, and that each subsequent number is strictly larger than the last. This is what we call a model for the axioms of our theory. Specifically, using this model, all of the axioms I asserted are true. Now, since 2 is strictly greater than 1, and 1 is strictly greater than 0, we have that 2 is strictly greater than 0, so this tells us in particular that 2 is not equal to 0 in this integer model of an integral domain. Since the freshman's dream fails to hold in the integral domain of integers, this also proves that the freshman's dream is completely unprovable from the axioms of an integral domain. However, this doesn't mean that we can prove that the freshman's dream is false only using the axioms of an integral domain. Let's play the same trick in reverse. Let's construct another model that satisfies all the axioms of an integral domain, but also satisfies that 2 equals 0. We can do this by taking an existing model of an integral domain and then force that 2 equals 0. If 2 is equal to 0, then by adding 1 to both sides, this means that 3 is equal to 1. Adding 1 again, we get that 4 is equal to 2. In other words, 4 is also equal to 0. Adding once more, 5 equals 3, and therefore 5 equals 1. If we keep repeating this, you'll notice that n is equal to 0 whenever n is even, and n is equal to 1 whenever n is odd. So, my model of an integral domain has only 2 elements. What about addition and multiplication? Well, we can use the parity rules that we learned in grade school. Restating these in terms of 1s and 0s, we get the following addition and multiplication tables. I'll leave the details for you to check, but this is indeed a model of an integral domain. This model is called the ring of integers modulo 2. In this model, we can see that x plus y all squared is actually equal to x squared plus y squared using the fact that 2 equals 0. In other words, we have just provided a model where the freshman's dream is true. This demonstrates that the freshman's dream can also not be disproven using the axioms of an integral domain. To summarize, because the ordinary integers do not satisfy the freshman's dream, we know that the freshman's dream cannot be proven using the axioms of an integral domain. On the other hand, because the integers modulo 2 do satisfy the freshman's dream, we also know that the freshman's dream cannot be proven false using the axioms of an integral domain. This imitates the general approach to proving independence, and this is also how we prove the independence of the continuum hypothesis. If you're still here, thank you for watching. If you liked the video, I hope you find a way of expressing that somehow. If you didn't like the video, then you serve as a model to demonstrate that the statement, "G's videos are enjoyable," is independent of the foundations of my channel. How? Well, I already have one model to demonstrate that the statement is consistent.